As we've been discussing constant coefficient homogeneous linear differential equations, we only looked at second order equations. But the tricks that we use actually work for any order of differential equations. So let's look at a higher order example. So here's a third order differential equation. It is linear homogeneous and has constant coefficients. And so the trick here is just to find the characteristic equation, just like for second order equations. So remember, the order of the derivative turns into the power on m. So we get m cubed minus 3 times m squared plus 4 times m minus 12 equals 0. So in principle, all we need to do is find all of the roots, real and complex, to this equation, and then use those roots to write down the solutions to the differential equation. One nice fact about polynomials with real coefficients is that if you factor them completely in complex numbers, you always get real roots or pairs of complex conjugate roots. Those are the only two possibilities. The real roots could be repeated, so could the complex conjugate roots for that matter. The examples that we've looked at in the second order differential equation case are really the only things that can happen, with the slight exception that if you have repeated complex conjugate roots, you have to use reduction of order, but just like before, you just get an x. So we can use what we know about second order equations to completely solve this sort of differential equation, as long as we can factor the left-hand side of our characteristic equation, or solve it for m. In practice, usually you would factor. I guess if it doesn't factor, you could use the cubic formula if it's degree 3, or the Korchak formula if it's degree 4, but if it's degree higher than that, factoring is your only hope. So let's go ahead and factor this characteristic equation to see what happens. It looks like these first two terms have a common factor, so why don't we group those? And these second two terms have a common factor, so let's group those. So in the first group, this factor out an m squared, so this is m squared times m minus 3 plus, and then in the second group, there's a common factor of 4, so 4 times m minus 3. And now the first term, this first big term, and the second big term, they have a common factor of m minus 3, so we can factor out m minus 3. And the stuff left over is m squared plus 4. Okay, so since we had a degree 3 polynomial equation here, we get 3 possibilities for m. This first one is m1 could be 3. Okay, now the other two, right, and I guess we could call them m sub 2 and m sub 3. These, right, if you set m squared plus 4 equal to 0, move the 4 over, and then take square roots, you get that the second two possibilities are actually an imaginary pair plus or minus 2i. Each of these possibilities for m gives us a solution to the original differential equation. So the real possibility for m gives us y sub 1 is e to the 3x, exactly as it would have in the second order case, right? Real solutions just give you exponentials. And this pair of complex conjugate solutions, just like in the second order case, a pair of complex conjugate values for m give you 2 solutions to the differential equation. And you know, the form of how you turn the value for m into the appropriate solution is exactly the same. So this doesn't have a real part, so our exponential is e to the 0, so 1 times cosine 2x, and the y sub 3 is sine 2x. So the general solution to the original differential equation would be c1 times y1, so c1 e to the 3x, plus c2 times y2, which is cosine 2x, plus C3y3, which is sine 2x. So you can see any linear homogeneous differential equation with constant coefficients of any order, in principle you can solve if only you could factor the characteristic equation. Now in practice that's quite difficult. I actually specially formulated this example to make this factoring doable. But in principle, if you can find the complex roots to the characteristic equation, you can write down all of the solutions to the differential equation.